Oui. We will not give this presentation in French because I cannot. Welcome to a slightly more technical presentation than we gave yesterday. We are going to talk about Android rendering. I am surprised to see so many people in the room.
If you're looking for funny talk, this is the wrong room.
If you're
Don't laugh, it's not going to be funny.
If you're tired and you would like to sleep a little bit later this morning, this may be the right room for you. We'll see how this goes. So we gave talks like this years ago, 5, 6, 7 years ago, to talk about how Android rendering works, and we talked about hardware acceleration. Some of those details have changed, so we thought it's been a while, we would update that and tell everyone everything that happens in Android rendering. However, that's way too much detail that we could go on and on and on. We will cover the basics today. We'd be happy to entertain questions, but I doubt that we will have time. Let's get started. So rendering, at least in English, the proper definition of rendering is melting fat. In order to clarify it, you take the cow and then you render the fat out. That's not actually what we mean today. Rendering this process, especially on Android, of turning the user interface into the actual pixels on the screen. So what are all the things that happen to make that button draw on the screen? So first of all, I'm going to use some visual cues in my slides because there are a lot of details to understand here. We'll have some dots at the top of the screen, a little color coding so you know what's going on. So let me walk through the overall process and then we'll get into the details of all of those steps as we go. So first of all, there's this thing that we call the choreographer, which on vertical sync, which is every single frame, there's a pulse down at the native layer where we find out, okay, this is the time when you should do everything. So we have this vsync happening roughly 60 times a second. So we get this pulse from the choreographer, and one of the things that it does is it collects all of the native input events, batches them up, and then sends it up to the Java layer, where we then receive those on the UI thread. So the UI thread wakes up on the vertical sync and says, okay, it's time to do some stuff. First of all, let me gather the input events and process those, figure out where the user clicked, dragged, moved, or whatever. Then it will process animations. If there are any happening, then those tend to change view properties, and then we need to react to those, redraw the views, do layouts, whatever it is. We do any measures that need to happen, asking the views how large the views would like to be when they draw, and then telling the view system how large those views should be and where they should be positioned on the screen. Again, I'm going to go more into the details of this as we go. Then we actually draw, which is the process of converting all of those canvas operations, how exactly do you want to draw that button, into a more native representation of how we're going to display the pixels on the screen. Then we synchronize over to another thread. The render thread is something that we created in the Lollipop release. It runs asynchronously from the UI thread, and that's the thread that we use to actually interact with the GPU. So we create all the rendering operations over on the UI thread, and then we synchronize, basically pass a handle off to the render thread, and then it does its work while the UI thread can go off and do other things. Execution is the process of taking this internal display list structure and turning it into something we call DL ops, or display list ops, and optimizing those, getting ready to then talk to the GPU a little bit later. We get the buffer, so we request from the GPU a buffer to actually put this information in there. Is anybody falling asleep yet? All right.
I am.
As I said, it gets a little detailed. And then we actually do OpenGL commands to talk to the GPU. And when we're done with that, we swap the buffer. We say, okay, we're all done. Now flip the buffer so that we can present these on the screen. And then that talks to the hardware compositor, which Romain is going to talk about later. So all the dots at the top of the screen are going to be sort of visual representations of where we're at in this entire flow. So let's walk through a couple of examples and see what actually happens. This is a simple example. Let's pretend.
A beautiful app created by Chet.
Yeah, this is a screenshot of an app that I actually wrote. I want credit for this. It's a recycler view app. There's some items in there. I'm sure this looks exactly like all of the applications that you write. It's just as complicated. The user is going to click on one of the items, and then for grins, I wrote some logic that will then change that item's background drawable to a different color. So we click, and then item color changes. So what are all the things that happen to make that happen? First of all, let's take a look at the representation of the view hierarchy. So if we look at the layout code, it is essentially this. And then I populate those items at runtime, just having some numbered items. Populate the recycler view in the middle there. The resulting view hierarchy, once those items are populated, looks like this. So the content that you're actually populating in there doesn't include all the action bar stuff. That's sort of pre-populated by the framework. What we do is we set the content view to essentially that hierarchy that we see on the right. So that's all the stuff that we care about there. That's what we're going to affect with the clicks and the drags and the moves, and that causes the invalidates and the measures and the layouts that we're going to walk through. So what happens when the user clicks? So they're going to press there. Eventually that's going to be noticed. There's going to be a vsync pulse on the choreographer. We're going to collect those input events, send it up to the native layer. UI thread wakes up and says, okay, there was some input operations. We see that this has been a click. This is actually, I'm simplifying this a little bit. A click is not just an atomic operation. Obviously there was a down and then there was an up, and that gets recognized by a click. Slightly detailed, don't worry about that. But when we see that there's a click that has occurred, then we have some logic in my really complicated app that says, okay, I need to set the background color to a random value there. When I call set background color, that is a method on view, and it does some stuff to actually change the background color of that drawable, and then it calls this method called invalidate. Invalidation is the process of telling the view hierarchy that something has changed and something needs to be redrawn. We invalidate the content of that specific view, and then that propagates through the hierarchy so that the entire hierarchy knows that something has changed and needs to be redrawn so that we can put new pixels on the screen. So there's a click operation. We have that input thing there, and then we have an invalidate that happens on the view behind me right there. So that is the view whose content's changed. Because of the background color, it got invalidated, and then this becomes an invalidation operation that walks all the way up the tree. Now there's a difference between the invalidate call that got called on the view that changed and the invalidate calls that propagate up through the hierarchy. The one at the bottom says, I have changed, I need to be redrawn. All of the calls up the view hierarchy say, something below me changed, and we need to propagate drawing calls all the way down there. This is a important optimization that we've had in there since the early days, because we don't want to redraw everything just because that one item changed. But everybody at the top needs to know that somebody at the bottom changed so that they can propagate that logic all the way down to where it needs to go. So once it gets to the top, it ends up being code in a class that we like to call viewRootImpl, because that's what it's called. And it ends up in a method called invalidateChild, which basically means somebody in the view hierarchy has changed. And then we call a method called scheduled_traversals. And this is basically an asynchronous way of us saying, hey, something has changed. Go ahead and post an event there to make sure that we handle this thing. So there may be invalidates happening all over the tree everywhere. Each of those is going to propagate up to the top, result in a call to schedule traversals, which basically sets a flag and says, okay, at traversal time, you need to do something about that. We call scheduled traversals, and traversal is basically all of the important rendering steps. That's measure and layout and drawing. So it's those three phases together are what we call traversals. If you ever look through viewRootImpl.java, I wouldn't recommend it, but you could. Then you will see a method called perform traversals that basically does these three monolithic operations as part of it.
Actually, if you ever feel bad about the kind of code you write, go look at that method. You will feel a lot better about your own code.
And then once you conquer that, go look at something like Window Manager. Okay, so viewRootImpl, perform traversals, does the measure, layout, and more importantly, draw, because that's what happens when we cause an invalidate. The other ones don't kick in right now, but we do need to do a perform draw operation. Perform draw says, okay, I would like the view hierarchy to draw itself, and it sends that request in, and then there's a call to get display list. So a display list is an important concept in general in Android. It's something that kicked in the Honeycomb release when we first did hardware acceleration. It's a way for us to encapsulate the drawing information. Here, there's all the draw methods that get called by the canvas, but then there's a way of encapsulating that and recording those as a series of operations that can then be issued to the GPU. So display list is that encapsulation. It's all the rendering commands that have to happen to actually draw that view. So when we call display list at the top, this doesn't mean I need that decor view and linear layout and frame layout to redraw themselves to create their own display lists. Those display lists haven't changed. They did not get invalidated. Instead, they already have their own internal representation of their display list, and then they have references to any of their children. And then we propagate that display list call down to the bottom of the tree. We keep asking each of those parents for their display list, and eventually we end up at the bottom layer of the tree, and we ask the item that actually changed for its display list, at which point it says, oh, I was invalidated, I need to redraw myself. So it redraws itself, which results in something like this. So in the case of the simple item, it's going to draw a rectangle and it's going to draw some text. Rectangle with that new color, the text with the text that was already there. This results in a data structure, something like this, a display list representation that says I have a rectangle and I have some text with a string in it. And then that propagates all the way up to the top so that the final result is a display list for the entire view hierarchy, which is a hierarchy of display lists, which contains the new display list that was just produced at that bottom level. At this point, we're ready to synchronize all of this information from the UI thread over to the render thread. We basically pass a handle over so that the render thread can then talk to the GPU and actually process those display lists. So we have the UI thread representation of the display list hierarchy, and now we have a render thread representation of the exact same display list hierarchy, which we're then going to post-process. At that point, the UI thread is done. It can go off and do something else if it would like to, or just more regularly, it's just going to wait around for the next frame to happen, and then the render thread needs to do all of its work. It's important to note that we also pass over other information, including the damage area. So not only do we have the entire hierarchy of display lists, but we also know which area on the screen actually changed. So when we propagated that invalidate up from that single item, we also propagated the information about where that item was on the screen and how large it was, so that we know when we draw on the screen, we really only need to redraw in this little region. This is going to come up a little bit later. We use this information to optimize the amount of work that we're actually doing. So damage area, excuse me, this is also a time when we can do some optimizations, such as knowing, okay, there are some bitmaps that are new, maybe they're new glyphs, so the glyph cache is changed to draw some text. Maybe somebody is drawing some bitmap somewhere that needs to be uploaded to a texture, and then we upload those at the beginning of this frame to the GPU. That tends to take a bit of time, so we do it at the beginning. This says upload non-hardware bitmaps. It's important to note that in the O release, there's an API called hardware bitmap, which is a much more optimal way of dealing with bitmaps in general for some situations. Now you can create a bitmap that doesn't need to be uploaded to the GPU, it just lives on the GPU. So instead of having a software bitmap plus a texture taking up twice as much memory in general, now we have this one optimal format that you can use instead. So assuming you're not dealing with hardware bitmaps, this is the time when we upload those and create textures. So render threads, talked about this already. This is the part of the system that actually deals with talking to the GPU. Okay, so we've synchronized, and now we're on to the execute phase. The execute phase takes all of the information that we have from the display list as well as the damage area, and it creates what we call DL ops, or display list ops. So it takes this data structure and converts it into another data structure, because that's what software engineers do.
It's effectively going from a tree of display lists to a flat list of drawing commands.
And then it optimizes that as well.
Yeah, there's a number of optimizations that we do at that point. We're not going to explain those in detail today. We mentioned them 3 or 4 years ago at Google I/O. So we do things like, if you draw into a layer, if you have a hardware layer or a software layer, we move all those drawing commands at the beginning of the frame to avoid storing the GPU. That's also where we handle alpha properly, and we do a lot of reordering and batching of commands. So we're gonna look at a concrete example of that, but we do not do the actual drawing in the order that your app is doing it in its draw methods.
So we can see a simple representation of this, and then we'll see a more concrete example. So when we do reordering and batching, it's much more optimal for us to do all the similar operations at the same time. It avoids doing something called state switching with GL. We don't want to draw a rectangle and then draw some text and then sort of constantly change state. Instead, we would like to draw several rectangles of the same color and then draw text for a while.
It's not just avoiding state switches, it's also merging drawing commands together, so we can make only one function call to the GPU, because those function calls are extremely expensive in the OpenGL driver.
So the pseudo DL ops that we have here, if we do some reordering and batching, we may end up with a stream of commands that look like the ones on the right here, where we're going to do a bunch of fills first, then we're going to draw the text stuff, then we're going to draw the lines, the borders between the items. We can see a specific example in Gmail. We got a performance boost of, I don't know, 10%. It was fairly huge, like a millisecond out of every 16 millisecond long frame, just from doing reordering and batching. So this is prior to the work happening. You can see that as we walk through, let's see. No. Oh, it's running there? Oh, it's not running on my screen. All right, so we're drawing each of the individual items, right? We draw an icon, we draw this text, we draw that text, there's another icon, there's all these things happening one by one by one. But once we did reordering and batching, then it looks something more like this. So we're going to draw all the similar operations together, and you can see some of those go in as just single operations because we were able to create a single drawing operation where we shoved all the separate DL ops together.
And usually the reason why some operations cannot be merged together, you can see, for instance, the background of all the list items are drawn one after the other. It looks like they have a drop shadow and they slightly overlap each other. So because of that slight overlap, we cannot merge them together. We have to draw them one by one. So an optimization in Gmail here would be to get rid of that overlap at the UI toolkit level so we could optimize the drawing.
Okay, so we have the DL ops. We've reordered and batched these things. And we can now cull things out. So the damage area that I talked about before, it's obvious to us at this native layer that we don't need to redraw the entire area of the screen. Instead, all we need to do is redraw that one little piece in the middle, which means that all of the rest of those DL ops in the stream of information about the entire view hierarchy can just go away. And we optimize it to just the stuff that actually lands within the area that needs to be redrawn because it was damaged.
So this optimization is important because we already do this at the view level. A view is not going to send the drawing commands for stuff that is outside of the bounds of the view. But here we can do it at a very fine-grained level. For instance, when you draw text, we can reject each letter that would not be part of the dirty area.
So now we execute, so we're actually going to issue GPU commands. We do a get buffer. This is actually an implicit command, so as we start to issue GPU commands, these OpenGL commands to the GPU, then there will be a buffer that we get as part of that where we can draw into, we issue all the GL commands, and then we request a swap buffer. So we've done a bunch of GL, and now we say, okay, present it to the screen. And then we're into the composite stuff. You can think of it like this. There's these different surfaces on the phone. We have the navigation bar at the bottom, we have the status bar at the top, and then we have the actual content from the activity. These get composited by the hardware compositor, which Romain is going to talk about later, and then we end up with the final result there. Okay, let me talk through one more example and sort of take the other stuff as read, but see how we work through something a little more interesting. What if the user presses and drags? What happens? So at first, things simply move on the screen, and then if you keep dragging, a new item appears on the bottom. So phase one, if you're just moving things, they're going to press down. We're going to receive the input event. We're going to end up in a touch event call and say, okay, there was an action down. All we need to do is record the state and then come back later and see if anything changed. So there's no op, nothing actually changed on the screen. We don't need to do measure, layout, and draw. Nothing else happens. We come back on a future frame and say, okay, they've dragged a little bit further. Now what do we do about that? We end up in this action move block here, and excuse me, all we need to do is offset the top and bottom. So note that we're not actually redrawing views, we're simply moving information on the screen. So that says invalidate view property. This is an optimization of invalidate, so we're not causing a later draw. All we're doing is causing a reissue of display lists with different translation information to move them on the screen.
Yeah, so a big optimization we have in the platform is that the display lists are not only a series of drawing commands, they also have properties. We know the bounds of all the drawing commands for the display list. We know their location, we know their alpha, we know their rotation and all that. So when we do this move here, we're actually not reissuing the entire display list. We're not calling draw on the Java side. We're just poking inside the display list and changing the X and Y. So it's extremely efficient for us.
So that invalidate view property looks very similar to what happened before, except it's Much quicker, it just says, hey, we need to reissue a display list, so propagate that information up to the top. Again, schedule traversals is called to make sure that that happens. Then the draw operation needs to happen, it says perform draw, which simply asks for the display list which already exists, nothing changed. It's easy. We just synchronize that information over. The properties are already set correctly. Render thread takes over, and all the rest of the steps happen as before. All right, phase 2, now a new item appears. So they keep dragging, and all of a sudden we have this item 6 that's going to pop up at the bottom of the screen. What happens? A little bit more. Excuse me. So we track the inputs. We say, okay, action move. Something happened that's going to require us to now create and bind view information on there. We're going to end up in code in viewgroup.java that calls add view. Add view calls something called request layout, which is kind of the layout equivalent of invalidate. We're not just saying something has changed and it needs to be redrawn. We're saying something has changed in a view group, in a parent, and that parent needs to measure and lay out its children to figure out where to put things on the screen. So request layout is the process of basically propagating that information up through the view hierarchy, saying somebody's layout has changed and you need to deal with that. So there was a add view on the view group that results in a call to request layout on that view group, and request layout propagates all the way up. Again to view root impl, and request layout does exactly what invalidate did before. It says schedule traversals. We end up in perform traversals, except this time instead of just doing perform draw, we're going to do a perform measure and perform layout.
Yeah, there's a slight difference with invalidate. We have two different types of invalidate. Chet explained that we want to know what path to follow to find a view that was dirty. But in the case of layout, we have to mark all the parents as dirty when it comes to layout, because changing the size of one element at the bottom of the tree could change the size of everything else above. We have a number of optimizations in the platform to avoid doing that whenever we can, but we don't know that until we go back down through the entire tree.
This is one of the many reasons why layout is really expensive, and it's something that you should avoid when you don't need to. We do so internally when we can, but in your application, avoid layout when you can. There's a lot of work that happens. So there's 2 steps to layout. The first step is measure. This is going through the hierarchy and asking all the children how large they would like to be. And that starts with the child that actually changed, but then that, as Romain said, that may propagate to other parents. If that child changed its size, maybe siblings need to change their size to suit. And then the second step is layout. Now that we have all that information on how large all the views would like to be, now we can tell all the views how large they will be and where they will be positioned on the screen. So, perform traversals happens. That results in a call to measure, which propagates all the way down the tree. We ask everybody how large they'd like to be, including the new item on the right, which has caused all this consternation. And then there's a call to layout all the way down. Once we know how big everybody needs to be, then we are going to push a layout call all the way down. And once that's done, now this view actually exists and is in the tree, and now everything needs to be drawn. So drawing happens exactly as it did before. All we did this time was we needed to do the measure layout stuff first to figure out where to put stuff. There's one big caveat to this. This is a very simplified example where I walk through a full request layout operation. It turns out that recycler view is way better at this, and list view that preceded recycler view as well. It knows when there's a request layout at that local level how to handle that for all of its children, so it actually ends up not propagating that information all the way up. Instead, it can just create that new view locally, move other stuff around, and then not calls all that work up the view hierarchy.
So in one of the previous diagrams, Chet had this little box that said Composite. So once you're done drawing in your window, we have to send the content of that window to the screen somehow. And turns out this is not something we've ever talked about, I think, in any presentation before. It turns out that there's also a lot of complexity happening there. So we're going to talk about it today. So effectively, the problem we're trying to solve, we have a number of windows and we want to send them to the screen. So on Android, the window compositor is something called Surface Flinger. It's different from the window manager. The window manager is responsible for creating the windows, doing the layout, putting the views inside the window, but it's not doing anything related to the display or actual rendering. And on Android, a window is actually not a real object as far as we're concerned when it comes to composition. Instead, we talk about surface. So you probably have seen the Surface API when you use Surface View or some of the media API like the media codec or the media player. It's an abstraction that we use throughout the entire platform, and it's a very important one to understand. So before we understand how a surface works, we need to understand the concept of buffer queue. So buffer queue is what powers the entire graphics pipeline on Android. It's a fairly simple consumer-producer architecture. So a buffer queue is made of a number of buffers. So that makes quite a bit of sense. The number of buffers depends on how you configure the buffer queue. Sometimes it's 1, sometimes it's 2, sometimes it's 3. It really depends on what we're trying to do in the platform. Typically, for an application, when we're rendering on screen in a regular application using the UI toolkit, we have 2 or 3 buffers. If you want to understand why we have 2 or 3, we gave a talk, I think on Project Butter a few years ago when KitKat was released, where we explain the benefits of triple buffering and the drawbacks of triple buffering. So when a producer wants to create content, wants to put pixel on screen, he needs to get a buffer from the buffer queue. So for that, we call a function called DQ buffer. And when we call DQ buffer, we ask the buffer queue for a buffer with a given layout. That means a width, a height, a certain number of bits per pixel, all that kind of information. If the buffer queue has a buffer that matches those specifications, we get it right away. Otherwise, the buffer queue has to go talk to a driver in the system called Gralloc and ask for a new chunk of memory. So we're not going to talk about this. That's even more details that you really don't want to know about. So once you DQ the buffer, you own the buffer as the producer. So buffers on Android can be exchanged between applications and modules. They don't stay in place. So your producer can now draw, you can render content in many, many different ways. And when you're done with producing the content, you send it back to the buffer queue using a function called queueBuffer. And it's added at the bottom of the queue. Then the consumer can acquire a buffer. The buffer is moved to the consumer side. And the consumer can do whatever it needs to do with it. So in our case, it will be window composition. And again, when it's done, it releases the buffer and sends it back inside the buffer queue. So of course, under the hood, to make all that work properly, there's a lot of synchronization that needs to happen, especially because the 2 endpoints, the producer endpoint and the consumer endpoint of a buffer queue, can be in different processes. And that's the magic that powers everything graphics related on Android. So what happens when we actually create a window on Android? So the way a window is created, we actually have a publicly available API in Window Manager called add_view. You just add a view to the window manager and it creates a window on screen. So we have the window manager, it's going to be our producer. We want to create a window, so it talks to Surface Flinger, and Surface Flinger on the other end creates something called a layer. So a layer is for basically the equivalent of a surface or the equivalent of a window, but inside the compositor. The layer creates and owns the buffer queue. So here we already see that we have a consumer in one process, in the blue process, it owns the buffer queue, but the producer is in a different process, it's in the window manager process, and that's still not your application. So then the window manager will create a surface, which is the producing endpoint of a buffer queue. And that all ties together when you use, it's easier to understand when you use a surface view, for instance. So here we see the surface of your application. You have a regular activity. You add a surface view inside. So what we do is we poke a hole through the window. We just do a clear of that section. The window manager creates another surface, creates another layer inside the Surface Flinger, and just slides it under your window. So it looks like it's part of your window, it's part of your application, but it really isn't. Then you can use a graphics API like OpenGL or Vulkan to produce content in that surface. So the way it works is you DQ a buffer, you generate your content, and you queue the buffer back when you're done with your frame. Another concept that's widely used on Android is surface texture. So if you've used texture view, for instance, that's what powers texture view underneath. It works very similar. It's very similar. It's just a way of consuming a surface from OpenGL. So you have OpenGL content. You would like to display the content of another app as a texture. For instance, a video. You have a video player. You want to map that video on the cube or something. So you create a surface texture. The surface texture creates a buffer queue. And to produce content in that buffer queue, you create a surface object. So the surface object is connected to the surface texture object. And if this is confusing, that's because we're terrible at naming. The graphics team tried all the combinations of surface and queue and buffer, and we ended up with this kind of mess. So once you have a surface, but the important part is that the surface is always the way you produce content on Android. So you have your surface going to be the producer. And when the surface is done producing something, the OpenGL side can acquire a buffer from the buffer queue, for instance, a frame of a video, and map it to a rotating object, whatever. And when it's done, it can release it again. So texture view helps you by creating the surface texture on your behalf. The consumer in that case is the render thread that we mentioned earlier. And the surface texture is effectively treated as a hardware layer. So if you call view.setLayerType hardware, there's basically no difference really between that and a surface texture as far as the render thread is concerned. And the texture view is pretty much a fancy image view. Instead of displaying a bitmap, it's displaying something that's called a surface texture. And there's in our platform, there's a number of producer and consumers. So surface view is you can produce and consume content with it. We have the surface texture we just talked about. OpenGL or Vulkan are consumers. So Chet mentioned getting a buffer at some point in the life cycle of a frame. And this is called by calling DQ buffer when we do our first draw call to the driver. That can vary from driver to driver, but this is basically done transparently on your behalf by the GL driver. And when you call EGL swap buffer, so the swap buffer step of the lifecycle that Chet showed, we queue the buffer back inside the buffer queue, triggering a window composition. The media codec, when you encode or decode a video, it can be producing or consuming. We have the media player and so many more ways of doing this. So all those different APIs that you can find across different packages on Android are all based on those same basic concepts of buffer queue and surface. So here's how the composition actually works. So we have our layers, we have surface flinger, and we have the display. To talk to the display, we actually don't, there's actually another block called the hardware composer. So that's a special hardware block. It's not a GPU, it's something else. And it's a hardware abstraction layer. The hardware composer API is a hardware abstraction layer. It's device specific. Every device might have a very different way of doing this. So we have this very special API on Android we use to just ignore how the device does it. We don't want to know. And it varies so much from vendor to vendor that it would be impossible for us to implement it for every device out there. So the goal of the hardware composer is to skip the GPU to put the windows on screen. If we are to use the GPU to do the composition of the windows, we would take away a lot of bandwidth and computing power away from your applications, and we would get a lot of jank, we would slow down your animations and all that. So we use something called hardware overlays. You can basically imagine that the hardware composer is just a bleating engine. So it has 4 hardware bitmaps, for instance, and it can blend them together really quickly without using a lot of power and a lot of bandwidth.
Traditionally, there were 4 overlays, certainly in the time frame of sort of Honeycomb and ICS, it was pretty standard to have 4. Modern devices tend to have more, which is great, because if you have 4, think about it, we have navigation bar, status bar, activity content, maybe there's one more there. It was kind of easy to trip into requiring a 5th window in the screen.
We also have the rounded corners now. So if you have a Pixel 2 XL with the rounded screen, we actually draw rounded corners. The screen itself is rounded, but to make them look nicer and to have exactly the size we want, we draw our own corners, and those are extra windows that we have to put up on screen, and we want to make sure they go inside the hardware composer. So the hardware composer API is really a composition protocol, because even when a device has 4 hardware overlays or 8 hardware overlays, they don't all have the same capabilities. For instance, we have devices where 2 of the overlays can be rotated and the 2 other ones can be scaled. Or maybe you have 8 overlays, but they can't all be the size of the screen. So sometimes you have to use 2 overlays to composite only 1 window on screen. So this is very complicated, and this is why this is behind the black box as far as we're concerned. It's a driver that's implemented by the hardware vendors. So here's how it works. So we have Surface Flinger, we have a number of layers that have been produced by the UI toolkit or any other means. And we call prepare on the hardware composer. So here I'm using the hardware composer lifecycle of hardware composer 1. Now we use something called hardware composer 2, but it's much more complicated, so I'm not using it. But fundamentally it works the same way. So when we call prepare on hardware composer, it tells us which windows, which layers can be directly handled by the hardware composer. So it will tag every one layer and will tell us this one is an overlay, this one is an overlay, this one is an overlay, everything's an overlay. So Surface Flinger is basically done. Then we call set. We send all the layers to the hardware. and they go directly to the display. And this is the ideal case. This is where we want to be. That's why in the past we've told you, don't create too many windows on screen, because if you have too many windows, we won't be able to be in that good case where everything goes straight to the display. Now here's a case where not all the layers can be handled by the hardware composer. So we call prepare. The first layer can go inside an overlay, so that's great. Unfortunately, the next two are tagged frame buffer. So what that tells us is that the hardware composer doesn't know how to handle those layers, and we need to do it ourselves. So we mark our first layer as an overlay. Then we need to create another layer that we know can be handled by the hardware composer. We have a way of knowing that. And that's going to be our a composition target for the next two layers. So those two layers have to be sent to the GPU, and we're going to use OpenGL to do our own composition into that new layer we've created. So at the end, we're left with only two layers. We know they can go in the overlays, and we can send them to the display. And that's the key here, and that's why we don't want you to create too many windows, or why we are very careful with that, because when we have to add this extra OpenGL step, it creates, first of all, it's expensive because we have to run the GPU, so we use the shaders, but it also uses a lot of bandwidth because we have to make an extra copy. So we send the layers to the overlay, and everything goes to the display. And that's pretty much it. So several other things that are worth mentioning. We used to recommend to use the invalidate method that takes a rectangle, or the left, top, right, and bottom. It's now deprecated. A view is always fully invalidated. It's all taken care of by the render thread, so you don't really have to worry about this. The GPU is fast enough now that you shouldn't have to deal with it. And the main reason why this was deprecated was because it was difficult to get it right. Very often we would see small 1 pixel wide artifacts because of rounding errors in the computation of applications. And even the UI toolkit had a few bugs, and we've certainly had many bugs over the years. So we decided to just get rid of it and make things a little better.
There was work done with RecyclerView about a year or more ago doing prefetch at idle time. So we talked earlier about the UI thread doing a bunch of work and then synchronizing information over to the render thread, and then the render thread talks to the GPU. For the most part, in most situations, that's actually relatively serial process. We do a bunch of work to create the display list information, then the render thread does stuff, and there's nothing really more for the UI thread to do. However, it is possible for us to now do work in idle time. So after we've synchronized that stuff, there's some idle time where the UI thread isn't doing anything anyway. So now RecyclerView can take advantage of that and actually have callbacks into application code or framework code to actually prefetch information, sort of optimizing the multi-core situation that we have.
And there are other features of the graphics pipeline that we didn't talk about in details, but for instance, the concept of virtual displays. So you can create a virtual display, and it's a way to tell Android that you want to composite a set of windows inside your own buffer. So it doesn't go on screen, it goes inside your own buffer. We just mentioned that when we cannot send all the layers to the hardware composer, we have to do our own GPU composition. So a nice side effect of that is everything that the hardware can do, we have to be able to do anyway ourselves with the GPU. So the virtual display is what you use to do, for instance, picture-in-picture, or when we want to do Chromecasting or take a screenshot, we create this virtual display, and we ask Surface Flinger to do a composition without the hardware overlays most of the time into that buffer directly. We also have color transforms that are part of the hardware composer. Some of the color transforms we use, for instance, the nightlight mode, when the screen turns orange at night, that's part of a color transform that's handled by the hardware composer. The color management that we've added to Android O is also part of the color transform system. We have emulation of, we have special modes for color blindness. It's also handled by the color transform. So typically this one is fairly limited. We only have one color transform for the entire screen, so everything has to look the same. But we're trying to work with the vendors in the future to make that better.
Actually, one of the other details that I kind of wanted to integrate into this, but it was complicated enough already, is there's also the detail of how shadows get produced. It's really more of an implementation detail than you never need to worry about as a developer. But basically, once we have all the information in the DL ops about here's all the stuff that we're going to draw, well, we know the elevations of all of those views in the system. Therefore, we know the shadows that they're going to produce. And then we produce the shadows for the views as well as merge the shadows for views at the same elevation. And then it makes reordering and batching a really interesting problem to solve. But it's kind of an interesting detail about how that stuff actually gets produced at 60 frames a second.
And if you want to know more or to play with some of that stuff, there is a simple app called Graphica with a K that was written by someone from the graphics team a few years ago. And it shows you how to use surfaces and surface textures and virtual display and the media codec to create interesting things. For instance, when you do ADB shell screen record or you press the video record button in Android Studio, effectively what we're doing is create a virtual display, put all the windows in the virtual display, connect the producer end of the virtual display to the media codec to record the video. So we're not doing anything particularly crazy that you cannot do yourself. This is all available APIs. And we're done, so we have just 4 minutes left for questions. I think that means please shut up. Any questions? Or was it so clear that you understand everything? There's a question over there.
Curious about the render thread. I remember one of the things that it enabled in Lollipop was the creation of the ripple effects and a lot of the rich effects that came in Lollipop.
Go ahead, sorry.
Oh yeah, it doesn't seem like the render thread is doing all that much. So I'm wondering, like, what is the render thread doing that allows us to have such richer experiences?
So it's not, it didn't enable the creation of the ripples. What it enabled was the animation of the ripples uninterrupted by other things happening. Typically, the ripples are used when you tap a button, which will trigger an action in the application, like starting an activity, and that's very heavy. And I would just pause the animation that was running on the UI thread. So it was moved. We've had the idea of the render thread a long, long time ago, but we had no good reason to introduce that kind of complexity before. But the ripple was one of the deciding factors. And the render thread actually does a lot of work. Generating the DL ops, doing the batching, the merging. We have to generate meshes on the fly. We have to tessellate the shadows. We have to update the font cache. There is a lot of work happening on the render thread.
But it's a good question because all of that work, that's not new work that the render thread took on. That's work that used to happen in the single UI thread. We basically split out the bottom layer and pushed it over to this other thread, which if it didn't do anything more than that would be pointless. All we're doing is creating and running another thread, which just makes everything way more complicated. But the benefits were, exactly as you pointed out, the ripple, as well as circular reveal animations run atomically on the render thread, and also now animated vector drawables as of the O release, I believe. And they benefit from the same thing, which is they run asynchronously. They can keep running on the render thread even when something is stalled out on the UI thread. In an ideal world, we would allow all animations to run on the render thread. The thing that keeps us from doing that is our animation APIs allow application code to inject themselves into animations. We can call into your code. Render thread is a native level concept. It will not call into user code because we do not want to stall it out on anything. Well, so an arbitrary object animator can never run on render thread, but these specialized atomic animations can.
Well, not only that, but also certainly your code will be called from a different thread, which could lead to a lot of very fun bugs to debug.
We can take one more quick one. Yeah. Yes?
Thanks. You talked about the optimization for Gmail, and on what layer did you optimize the rendering of the vesicular view for Gmail? Was it on the frame bottom on the hardware, or was it for the vesicular view, or on which level?
So the answer is at all the levels. There is so much we can do. So we have all this, crazy logic inside the render thread to do this batching and this merging, and it's a lot of very complicated code. But it's very easy for an application to do something that seems completely innocent and that breaks all those optimizations. So typically what happens, when we look at what the render thread is doing, we can identify fixes that we can make at a higher level. So it's really like all those layers working together to bring the best experience possible. To be fair, nowadays, we don't look at those optimization in that much detail anymore because the GPUs are just so fast that we don't have to do crazy optimizations all the time. Now it's more about like the I/O, like doing I/O or networking on the main thread, or the problems with paging in recycler view. Those are this is the kind of focus we have nowadays, not really the rendering anymore.
The specific example we were calling out, though, was on render thread. It was once we have those DL ops that we've created from the display lists, then we can go ahead and optimize those and reorder those. So that's really at a very low-level implementation detail from the application's point of view.
But if you want to hear about other crazy optimizations we do, a few years ago I wrote an article on Medium that explains how we handle text in a render thread. That alone is it's like 12,000 lines of code. There's a lot of things happening. So if you're into that kind of things, you might find that interesting.
So that wraps up the questions. I would say thank you for coming, and very quickly I should point out that our teams are hiring. So if you found this interesting, please come talk to us. And if you did not, I don't know why you're still here. Thank you.
Oh.